Should I stay or should I go? Welcome to this web lecture on integer decisions in transport. So first let's look into what an integer decision is. For instance, an integer decision is how many containers shall I transport? An integer decision is shall I buy a second barge or should I pay for extra loading time at the port? However, those last two are actually a special case of an integer decision because the answer is either yes or no, or 0 or 1, but it cannot be 2. So how are we going to tackle this? We're going to look at an example. So when we looked at linear programming, we're looking at the example of a barge transporting sand and coal, so a barge like the one on top. Now we're going to look into the lower case, so container-based transport. In our example that we looked at before, we had a barge that transported sand and coal at certain revenues. The barge was capacitated, so we were not able to load more than 225 tons of either sand or coal. We had some additional restrictions on, for instance, coal availability and the time that it took us to turn over this barge. Now what we're going to do is we're going to slightly adapt this example to container-based transport. So now we have a barge that can transport 20 or 40 foot equivalent containers at revenues of 100 and 150 euros per item. The nice thing about these 20 and 40 foot containers is that if I put two 20 foot containers there, I can put a 40 foot container on top. And so we can, for instance, give the capacity in 20 foot equivalent containers. So we can load 40 20-foot containers or 20 40-foot containers, or any combination of the two. Secondly, we have a loading time constraint. So if we load a 20-foot containers, this takes us 2 minutes, while loading a 40-foot containers just takes us a little bit more because we have a little bit of additional activities that we have to perform, and it takes us 2.2 minutes. This barge now has to be turned over in 60 minutes. So after 1 hour, we must have loaded everything that is going to go onto this boat. So what is the problem that we're trying to solve? We would like to find the revenue optimal number of containers per type. So not as in the sand and coal case where we wanted to find the revenue optimal amount. Now we're trying to find the revenue optimal number. What do we need to consider? So obviously we still have the capacity constraint and the loading time constraint, but additionally we have integrality. And I will show you in just a slide from now what this actually means. And lastly, how can we solve this problem? So we're solving this problem visually using two variables again. So you've seen this case in the linear programming web lecture already. So here we have the number of 40-foot containers on the x-axis and the number of 20-foot containers on the y-axis. And then we plot the constraints. So the availability or the capacity constraint and also the loading constraint. And if we solve this, we get this shaded blue feasible area. And we get an optimal solution of 1.1 40-foot containers and 1.7 20-foot containers at a revenue of 344 euros. Now let's look at this. This doesn't feel well, because if we want to load 1.1 40-foot containers, what we have to tell our customers, yes, so this container we can fully load, that's not an issue. But from your next container, we can load this small bit, but this large part of your container is on the next chip. And if you think a little bit about what this means, that means that you have to cut through a container, which is obviously nothing that you want. So what you additionally need to restrict yourself to points where you have integrality on both the number of 40-foot and the number of 20-foot containers. So in this visual representation, this means that actually only the points, the dots in this graph are optimal and not the entire blue shaded area. So now, since we have a relatively small example, we can just have a table. This table has the 20 and the 40-foot container number and gives us the solution value. And what we see here is that we have two solutions where we obtain a revenue of 300, while all others obtain a revenue that is lower. So either we ship two 40-foot containers or we ship three 20-foot containers, but we actually do not mix. So now we know the best solution of the integer program. We also know the best solution of the linear program, and now we're trying to compare them. And we're comparing them with a metric that is called the integrality gap. The integrality gap describes how much worse the linear program is actually relative to the integer program. That sounds a little bit confusing because here it looks like, of course, the linear program gives us the better value, but of course the linear program is worse at describing the problem, and this is what the integrality gap states. It states how much worse is the linear program at describing the actual problem. So let's look at this. The integrality gap is defined as the objective value of the linear program divided by the objective value of the integer program minus 1. So if you put in the values, so 344 and the 300, then we get a gap of 14.8% roughly. So one thing that you have to remember, currently we're maximizing. If we were to minimize, then we would have to, in this equation, revert the integer and the linear solution. So if we have had a minimization problem, our gap would be the objective of the IP divided by the objective of the LP minus 1. So how can we get from this linear program to the integer program and to the optimal solution in there? So the first thing that we can do if we have a linear program is we can round, or we can also use heuristics. However, those of course don't necessarily give us the optimal solution. But the good thing is that Garobi, Cplex, etc., they have implemented a lot of very efficient algorithms that actually give us the best solution rather than just enumerating all points as we did in the visual solution. And two examples are branch and bound and cutting plane. I will not go into detail on these methodologies during this web lecture series, but if you're interested, you can read up on these and find out a little bit more on how they work. What I would like you to take away from this web lecture on integer decisions is, first of all, the example of container transport, which will pop up during multiple future web lectures. Secondly, I would like you to remember the graphical solution. Thirdly, I would like you to know what the integrality gap is. And what I would like you to look forward to is modeling MILPs, which we're going to do in the next video. Thanks.